Welcome to this walkthrough of problem number 1245, tree diameter. In this session, we'll explore the problem, break it down step by step, and look at an effective approach to solve it. Let's get started. In this problem, we are tasked with finding the diameter of a tree. A tree is a type of graph that is connected and contains no cycles. The input is given as a list of edges, where each edge is represented by a pair of nodes, U, V, indicating an undirected connection between these two nodes. Our goal is to calculate the diameter of the tree, which is defined as the length of the longest path between any two nodes in the tree. It's important to note that this path does not necessarily have to pass through the root of the tree. For the input format, we are provided with an edge list, where there are n1 edges for a tree with n nodes. Each node is numbered from 0 to n1. The output will be a single integer representing the diameter of the tree. Let's look at an example. Suppose the input is edges equals 0, 1, 0, 2. This means we have a tree with three nodes, 0, 1, and 2, where node 0 is connected to both nodes 1 and 2. The tree can be visualized as having node 0 at the center with two branches. The longest path in this tree is between nodes 1 and 2, which passes through node 0. The length of this path is 2, so the output is 2. This demonstrates how the diameter of the tree corresponds to the longest path between any two nodes. Now, consider another example with the input edges equals 0, 1, 1, 2, 2, 3, 1, 4, 4, 5. Here, the tree has 6 nodes and can be visualized with node 1 serving as a central hub. From node 1, there are branches leading to nodes 0, 2, and 4. Node 2 extends further to node 3, and node 4 extends to node 5. The longest path in this tree runs from node 3 to node 5, passing through nodes 2, 1, and 4. The length of this path is 4, and therefore, the output is 4. This example highlights how the diameter can span multiple branches of the tree structure. Finally, let's discuss some constraints and edge cases for this problem. The tree will always have between 2 and 10⁻4 nodes, and the number of edges will always be n1, ensuring it is a valid tree. Each edge connects two distinct nodes, and the graph is guaranteed to be connected and acyclic. For edge cases, if the tree has only 2 nodes, the diameter is always 1 because there is only one edge. In a linear tree, where nodes are connected in a straight line, the diameter is n1, which is the total number of edges. In a star-shaped tree, where one central node connects to all other nodes, the diameter is 2, as the longest path runs between any two leaf nodes through the center. These scenarios ensure we account for both typical and special tree structures when solving the problem. To understand how to approach the problem of finding the tree diameter, let's first consider the brute force approach. The intuition here is straightforward: the diameter of a tree is simply the longest path between any two nodes. Using this idea, we could calculate all pairs' longest paths and take the maximum. One way to implement this is to use depth-first search, or DFS, starting from each node to determine the longest path to every other node. Alternatively, breadth-first search, or BFS, could be used for the same purpose. However, while this method is simple to grasp, it comes with a major drawback. Since we are performing a DFS or BFS from every single node, the time complexity becomes n squared, where n is the number of nodes in the tree. For small trees, this might be acceptable, but for larger inputs, the redundant computations make this approach inefficient and impractical. We need a more optimized solution that avoids these repeated calculations. A more efficient strategy involves using the two-pass DFS approach. The key insight here is grounded in graph theory. The diameter of a tree can be found by performing two DFS traversals. We begin by picking an arbitrary node and performing a DFS to find the farthest node from it. Let's call this node A. Next, we perform another DFS starting from node A. The farthest distance obtained in this second traversal represents the tree's diameter. This works because the first DFS guarantees that node A is at one endpoint of the diameter, and the second DFS ensures the longest path from A is the diameter itself. To implement this, we use adjacency lists to represent the tree and execute the two DFS traversals as described. The time complexity here is n, since each DFS traversal processes all nodes exactly once. This makes the algorithm highly efficient. Additionally, we can adapt this approach to use BFS instead of DFS. BFS is particularly useful for finding shortest paths in unweighted graphs, and it can be applied in a similar way to compute the tree diameter. The overall complexity remains O(n), but BFS may be easier to implement iteratively, especially if stack space constraints make recursive DFS less suitable. Having reviewed the options, the two-pass DFS approach stands out as the optimal choice. This method is both efficient and intuitive, leveraging the properties of trees, namely, their connectedness and lack of cycles, to compute the diameter in linear time. By focusing only on the two endpoints of the diameter, it avoids the redundant path calculations that make the brute force approach inefficient. While BFS is another valid choice, DFS is preferred here due to its simplicity in handling depth calculations. Its recursive nature is well suited to the problem constraints. There are a few key observations that make this approach particularly elegant. First, the tree's diameter always passes through the farthest node from any arbitrary starting node. Second, performing two DFS traversals guarantees we compute the diameter efficiently in linear time. Finally, since trees lack cycles, we avoid the additional complexity that would arise in general graph diameter calculations. As for trade-offs, both DFS and BFS are efficient, but DFS is often simpler to implement recursively, whereas BFS might be a better choice in environments with limited stack space. Compared to the brute force method, the optimized approach not only saves computation time but also scales well for large trees. In conclusion, the two-pass DFS approach strikes an ideal balance between efficiency and simplicity, making it the best solution for the tree diameter problem. It leverages the unique properties of trees to compute the diameter in linear time while keeping the implementation straightforward. This combination of theoretical soundness and practical efficiency makes it a reliable choice for solving this problem effectively. The problem we need to solve is finding the diameter of a tree, which is the longest path between any two nodes in the tree. Here, the tree is represented as an undirected graph with n nodes and n1 edges. This structure ensures it's a valid tree, as there's exactly one path between any two nodes. To solve this, we use an optimized approach based on two depth-first searches, or DFS. The key idea is that the farthest node from any starting point in the tree must lie on its diameter. We'll begin by representing the tree as an adjacency list, which is an efficient way to store the graph and provides constant time access to the neighbors of each node. This structure will form the foundation of our algorithm. Once the tree is represented as an adjacency list, the first DFS focuses on finding the farthest node from an arbitrary starting node, typically node 0. As we traverse the tree, we maintain a distance array to track how far each node is from the starting point. Using either a stack or recursive calls, we update this array as we explore new nodes. By the end of this traversal, the node with the maximum distance from the starting point is identified as the farthest node. This node is guaranteed to be one endpoint of the tree's diameter. Then, we move to the second DFS, starting from this farthest node. In this step, we again compute distances for all nodes, and the maximum distance encountered during this traversal gives us the diameter of the tree. Finally, this maximum distance is returned as the result. To understand why this approach works, consider the key insight: the farthest node found in the first DFS must be an endpoint of the diameter. This is a property of trees, where the longest path always passes through such endpoints. The second DFS uses this endpoint as a starting point to calculate the exact diameter. This 2DFS approach is efficient because each traversal visits every node exactly once, leading to a time complexity of O(n). The space complexity is also O(n), due to the adjacency list and the stack or recursion used during traversal. For edge cases, if the tree has a single node, the diameter is 0. In a linear tree, the diameter is the number of nodes minus 1, while in a balanced tree, the diameter stretches along the longest branch. This efficiency and versatility make the algorithm well suited for this problem. The algorithm relies on three key data structures. First, the adjacency list provides an efficient way to represent the tree, as it minimizes memory usage and allows constant time access to neighbors. Second, the distance array keeps track of the shortest distance from the starting node during each DFS traversal, ensuring we can identify the farthest nodes. Finally, DFS traversal is implemented using either recursion or an explicit stack. While recursion is often more intuitive, using a stack avoids potential recursion depth issues in large trees. To visualize the algorithm, think of the first DFS starting at node 0 and exploring all its neighbors to find the farthest node, which we'll call farthest_node. The second DFS then begins at farthest_node and explores the tree again to find the maximum distance to any other node, which gives us the diameter. Let's walk through an example to solidify the process. Consider a tree with 5 nodes and edges represented as 0, 1, 1, 2, 1, 3, 3, 4. First, we perform DFS starting at node 0. The distance array updates as we explore, and by the end, it reads 0, 1, 2, 2, 3. The farthest node from node 0 is node 4. Next, we perform a second DFS starting at node 4. This time, the distance array updates to 3, 2, 3, 1, 0. The maximum distance in this array is 4, which is the diameter of the tree. In terms of complexity, each DFS runs in O(n) time, and the space complexity is also O(n), due to the adjacency list and stack or recursion usage. This example demonstrates how the algorithm efficiently calculates the diameter, even for larger trees. To calculate the diameter of a tree, we start by importing the necessary modules, including default dict for creating an adjacency list and dict to facilitate breadth-first search, BFS. Inside the solution class, the tree diameter method begins by checking if the input list of edges is empty. If it is, the tree diameter is 0, and we return immediately. Next, we construct the adjacency list representation of the graph. This is done by iterating through each edge, where nodes U and V are connected bidirectionally. This adjacency list will allow us to efficiently traverse the tree. Now, we define a helper function called BFS, which will perform a breadth-first search starting from a given node. It uses a queue initialized with the starting node and a distance of 0. During the BFS, we also maintain a set of visited nodes to avoid revisiting them. The function keeps track of the farthest node encountered during traversal, as well as the maximum distance from the starting node. As we process each node, we explore its neighbors. For any unvisited neighbor, we add it to the queue with an increment distance to continue the traversal. When exploring a neighbor during the BFS, if the current distance plus 1 exceeds the previously recorded maximum distance, we update both the maximum distance and the farthest node. Once the BFS completes, the function returns the farthest node and its distance from the starting node. Using this helper function, we proceed to find the tree diameter. The first BFS starts at an arbitrary node, here chosen as node 0. This helps us determine one endpoint of the longest path in the tree, which we call node_A. Then, we perform a second BFS starting from node_A. This BFS identifies the farthest node from node_A and calculates the maximum distance, which represents the tree's diameter. Finally, the tree diameter method returns this diameter as the result. Here, we begin by importing the necessary classes and defining our solution class. The main function, tree diameter, takes a 2D array of edges as input and returns the diameter of the tree. First, we handle the edge case where the input is null or empty, and in that scenario, we simply return 0. After that, we construct the adjacency list representation of the graph using a hash map. Each edge connects 2 nodes, so for each pair in the edges array, we add the connection to the adjacency list for both nodes. This allows us to represent the tree as an undirected graph. Next, we define a helper class BFS result to store the results of our breadth-first search, which includes the farthest node and its distance from the starting node. Finally, we set up our BFS function, which will allow us to perform a traversal starting from a given node to determine the farthest node and its distance. In the BFS function, we begin by initializing a visited set to keep track of nodes we've already processed and a queue for the BFS traversal. Each element in the queue is an array containing the current node and its distance from the start. Initially, we add the starting node with a distance of 0. We also initialize variables for tracking the farthest node and the maximum distance encountered during the traversal. Inside the while loop, we process each node in the queue by removing it and marking it as visited. For each neighbor of the current node, if it hasn't been visited yet, we add it to the queue with an increment distance. If this new distance exceeds the current maximum distance, we update the farthest node and the maximum distance. Once the queue is empty, the BFS function returns a BFS result object containing the farthest node and the maximum distance from the starting node. With the BFS function defined, we can now proceed to calculate the tree diameter. First, we perform a BFS starting from an arbitrary node, in this case, node 0. The result gives us the farthest node from this starting point. Using that farthest node as the new starting point, we perform a second BFS. The result of this second BFS provides the maximum distance between two nodes in the tree, which is the tree diameter. Finally, we return this distance as the result. This approach ensures that we efficiently compute the tree diameter using two breadth-first searches, leveraging the fact that the longest path in a tree can be found by performing BFS twice, starting from any node. We begin solving the problem with a small tree example, where the input is a set of edges, 0, 1, 1, 2, 1, 3. The first step is to build a graph representation using an adjacency list. This helps us efficiently store and traverse the tree structure. After constructing the graph, we see that node 0 connects to node 1 connects to nodes 0, 2, and 3, and so on. Next, we perform our first breadth-first search, or BFS, starting from node 0. Initially, we set up a queue with node 0 and a distance of 0 and mark it as visited. As we process node 0, we visit its neighbor, node 1, updating its distance to 1 and adding it to the queue. Continuing, we process node 1 and visit its neighbors, nodes 2 and 3, updating their distances to 2. With this, the queue now contains nodes 2 and 3, both at a distance of 2, ready to be processed next. At this stage, we process nodes 2 and 3 from the queue, but since they have no unvisited neighbors, the BFS ends. The farthest node from our starting point, node 0, is node 2, which is at a distance of 2. Next, we perform a second BFS starting from this farthest node, which is node 2. Again, we initialize the queue with node 2 at a distance of 0 and mark it as visited. As we process node 2, we visit its neighbor, node 1, updating its distance to 1. Node 1 is then added to the queue. Moving on, we process node 1, visiting its neighbors, nodes 0 and 3, and updating their distances to 2. Both nodes are added to the queue for further traversal. Finally, we process nodes 0 and 3, but no new neighbors are discovered, so the BFS concludes. The farthest node found in this traversal is node 3, which is at a distance of 3. This distance represents the diameter of the tree, so the output is 3. Now, let's analyze a linear tree example with edges 0, 1, 1, 2, 2, 3, 3, 4. As before, we start by building the graph representation, which shows each node connected to its immediate neighbors. Node 0 connects to node 1 connects to nodes 0 and 2, and so on, forming a chain-like structure. Then, we perform the first BFS starting from node 0. During this traversal, we process nodes sequentially, first node 0, then node 1, followed by nodes 2, 3, and finally 4. At the end of this BFS, the farthest node from our starting point, node 0, is node 4, which is at a distance of 4. With this result, we initiate a second BFS starting from node 4. This time, the traversal proceeds in reverse order, visiting nodes 4, 3, 2, 1, and finally 0. The farthest node from node 4 is node 0, which is also at a distance of 4. Hence, the diameter of this linear tree is 4, and that becomes our output. Finally, let's consider a star-shaped tree example, where the edges are 0, 1, 0, 2, 0, 3, 0, 4. Once again, we begin by constructing the graph, which reveals a central node, 0, connected to all the leaf nodes, 1, 2, 3, and 4. In this structure, each leaf node only connects back to the central node. For the first BFS, we start from the central node, 0. During this process, all the neighbors, nodes 1, 2, 3, and 4, are visited in a single step, with their distances updated to 1. Any of these leaf nodes can be considered the farthest node at this stage. Next, we perform the second BFS starting from one of these leaf nodes, say node 1. From node 1, we visit the central node, 0, updating its distance to 1. Then, we traverse the remaining neighbors of node 0, namely nodes 2, 3, and 4, updating their distances to 2. The farthest node found in this traversal is any other leaf node, such as node 2, at a distance of 2. Therefore, the diameter of this star-shaped tree is 2, and that is our final output. To analyze the time complexity of the tree diameter solution, we start with the graph construction step. Here, we build an adjacency list representation of the tree, which involves processing each edge exactly once. Since there are e edges in the graph, constructing the adjacency list takes O(e) time. Next, we consider the breadth first search, or BFS, operation. In a tree with n nodes and e equals n1 edges, visiting each node takes O(n) time, as each node is processed exactly once. Additionally, during the traversal, we iterate over all edges to explore the neighbors, which also takes O(e) time. Given that e equals n1 in a tree, this simplifies to O(n). Therefore, a single BFS operation has a time complexity of O(n). Now, the algorithm we use performs two BFS traversals. The first BFS starts from an arbitrary node to find the farthest node, which we'll call node_a. The second BFS begins from node_a and determines the tree's diameter by calculating the maximum distance from this node. Since each BFS operation independently takes O(n) time, performing two BFS traversals results in a combined time complexity of O(n) plus O(n), which simplifies to O(n). When we combine this with the graph building step, which is O(e), the total time complexity of the algorithm becomes O(e) plus O(n). Given that e equals n1 in a tree, the overall time complexity is O(n). Next, let's look at the space complexity of this solution. First, the adjacency list used to represent the graph requires space proportional to the number of edges, which is O(e). Since e equals n1 for a tree, the graph representation consumes O(n) space. Then, we have the BFS queue, which temporarily holds nodes during traversal. At most, this queue will contain O(n) nodes, as each node is enqueued only once. Finally, the visited set, used to track which nodes have already been processed, also requires O(n) space. When we add up these components, the total space complexity of the solution is O(n) for the graph, O(n) for the BFS queue, and O(n) for the visited set, resulting in an overall space complexity of O(n). When comparing to a brute force approach, we see a clear advantage in efficiency. A naive solution would calculate the distance between every pair of nodes in the tree to find the maximum distance or diameter. This would involve performing a BFS or DFS from each of the n nodes, leading to a time complexity of O(n squared). In contrast, the optimized double BFS approach reduces this complexity to O(n), which is a significant improvement for larger trees. This optimization is based on the mathematical property of trees: the longest path, or diameter, always starts and ends at the farthest nodes. The first BFS identifies one endpoint of this longest path, and the second BFS computes the diameter, ensuring correctness in linear time. Whether the tree is a simple path graph, star-shaped, or balanced, the BFS-based algorithm maintains a time complexity of O(n), making it efficient across all scenarios. In summary, the time complexity of the optimized solution is O(n), and the space complexity is also O(n). This linear performance makes the algorithm highly scalable and well-suited for large trees. Compared to the brute force approach, which has a time complexity of O(n squared, the double BFS method is far more efficient. It balances both time and space requirements effectively, providing an optimal solution for the tree diameter problem. When solving tree diameter problems, there are several common mistakes to watch out for. One frequent error is confusing the tree's diameter with its depth. Remember, the diameter is the longest path between any two nodes in the tree, while depth is the longest path from the root to a leaf. Mixing these up can lead to flawed logic. To avoid this, it helps to visualize the problem and clearly differentiate between the two concepts. Another mistake is relying on brute force solutions, such as calculating all pairs' shortest paths, which can be computationally expensive in trees. Instead, leverage properties of trees, like using a two-pass DFS or BFS method, to achieve an efficient solution. Additionally, incorrect base cases in a recursive depth-first search can cause runtime errors, especially when the tree is empty or has only one node. Always account for these scenarios in your base cases. Lastly, in DFS-based approaches, it's easy to update the diameter locally without keeping track of the global maximum. To fix this, use a global or class-level variable to ensure the diameter is updated correctly across all nodes. Now, let's consider another common pitfall: ignoring node or edge weights in problems that require them. If the tree has weighted edges, failing to include those weights in your calculations will lead to incorrect results. Always read the problem statement carefully to determine if weights are a factor and adjust your logic accordingly. In interviews, it's helpful to demonstrate a solid understanding of tree properties, like knowing that the sum of degrees equals twice the number of edges. These fundamentals often underpin tree-related questions. Mastering techniques like the 2-pass DFS or BFS method is also essential, as it offers an efficient way to compute diameters. Interviewers may also test your grasp of edge cases, such as handling single-node trees, completely unbalanced trees, or trees with varying weights. Being able to discuss trade-offs is another valuable skill. For instance, you might compare brute force approaches to optimized ones, explaining why the latter is more efficient. Lastly, recursive DFS is a common implementation for tree problems, so practicing recursion and debugging recursive code will give you a significant advantage. Building on this, there are several related problems that can help you deepen your understanding of tree diameters. For instance, LeetCode problem 543, diameter of binary tree, is directly related and provides an excellent starting point for practicing tree diameter concepts. Similarly, problem 124, binary tree maximum path sum, involves finding the maximum sum path in a tree, which uses similar logic to diameter calculations but focuses on sum rather than distance. Problem 110, balanced binary tree, is another useful exercise, as it requires depth calculations, which are often tied closely to diameter logic. Finally, problem 1123, lowest common ancestor of deepest leaves, involves finding relationships between nodes and their depths, offering another perspective on how to approach tree-related problems. These problems will help you refine your approach and build confidence in tackling tree diameters under various constraints. To solve tree diameter problems, there are multiple approaches you can consider. The 2-pass DFS method is both efficient and intuitive. The first DFS identifies the farthest node from an arbitrary starting point, and the second DFS calculates the maximum distance from that farthest node. This approach runs in O(n) time and is straightforward to implement, though it does require two separate traversals of the tree. Alternatively, you can use a single-pass DFS with a global diameter variable. Here, you calculate the depth of each subtree while simultaneously updating a global variable to track the maximum diameter. This method is also O(n) in time complexity and is memory efficient, but it can be more challenging to debug, especially for beginners. For more advanced scenarios, such as weighted or directed trees, dynamic programming on trees can be a powerful approach. By storing subtree results, you avoid redundant calculations, which is particularly useful when path computations overlap. However, this method is more complex to implement and may feel less intuitive compared to DFS solutions. Each of these approaches has its strengths, so understanding their trade-offs will help you choose the right one for the problem you're solving. Great job on making it to the end. To summarize, we explored the tree diameter problem, discussed an initial brute force approach, and emphasized the importance of understanding tree traversal. Remember to keep practicing and refining your problem-solving skills. Thanks for tuning in, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!